I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students. Just ask you to bless this class, Lord, and just help us to understand a little bit more about your creation together, Lord. In your name I pray. Amen. So I introduced the rudiments of variational calculus and what's called Lagrangian mechanics last time. So I just wanted to just take a few more minutes of our time and show you a kind of non-trivial application of this to a problem you've studied in physics. If you've had physics, most of you had, I think. So you've studied like gravitation of a star and a planet, right? This is, more generally, this is called the central force problem. It involves some sort of interaction between, say, two masses, m1 and m2, where the force between them just depends on the radial distance between these masses, and it also is directed along that line of connection. So this is what's called the central force. So to solve the central force problem, what you do is you introduce some kind of sneaky coordinates. You use what are called center of mass coordinates and then relative coordinates. So the center of mass is 1 over m1 plus m2, m1r1 plus m2r2. So this basically is, if you want to think about m1 and m2 as a single particle, effectively it's like a single total mass of m1 plus m2 right there. That's what we learn in physics. And then you can also talk about this relative vector r12, which I'll take as r2 minus r1 as r. So we suppose basically that the force of interaction strength depends only on the distance. And we define r to be this. This is the relative coordinate. And then, so we have the following fundamental transformations. R is r2 minus r1, and here's the center of mass coordinate, which is this. You can take these equations and you can solve them for r1 and r2, and you get that. All right? And then, of course, r1 and r2, then you can also define relative velocity. And so this is the velocity of the center of mass. Here's the velocity, the relative velocity. And these are related to the constituent velocities v1 and v2 by these rules as well. And so you can calculate the Lagrangian, all right, as follows. So just, sort of basic, just like we did last time, the kinetic energy, 1/2 mv squared plus 1/2 mv squared. So like kinetic energy for the first mass, kinetic energy for the second mass. And this would be the potential energy relative to the central force, right? So the gradient of this potential function would give you the force of attraction or repulsion between these two masses. So you can rephrase the Lagrangian in terms of the center of mass velocity and the relative velocity. And when you do, you get this expression. So 1/2 the total mass, center of mass velocity squared, and then over here, this funny looking expression. Oh man, no. Oh. This funny looking expression times relative velocity squared, speed squared, right? And then potential energy. So you can see that this is behaving like a mass, right? This is behaving like a mass relative to some like new coordinates, where this is the velocity and that's the velocity. Of course, this is just total mass. This guy right here is what we call the reduced mass. So in this problem, usually people use like a mu for this, the so-called reduced mass. So if you introduce those symbols, which I will, algebra step, right? Kind of nice, that's better. So here it is. The Lagrangian in the center of mass and relative coordinates, it's 1/2 total mass, total velocity of center mass squared, plus 1/2 reduced mass velocity, relative velocity squared minus the potential energy, where I've defined these expressions. So typical application would be maybe you make mass 1 the sun, you make mass 2 the earth, right? Then in that case, the the reduced mass is what? Mass of the earth, mass of the sun, divided by mass of the earth plus the mass of the sun. So since the mass of the earth is kind of tiny, right, 10 to 10 to the 31st versus 10 to the 24th, right? I forgot. I don't know. It's been a few years. Am I right? See these useless numbers I remember still. Don't ask me my children's birthday. I haven't worked enough problems in those. Let's see here. Let's see here. Oh no. I'm supposed to hide these. I'm supposed to hide these sorts of personal data. Let's see here. So those cancel, and you see. So basically, the reduced mass is the mass of the Earth to a good approximation, and the center of mass is where the sun is positioned, and the relative mass is, well, I mean, so anyway. All right, so here are the equations of motion. So we have 1, 2, 3, 4, 5, 6 coordinates, right? Position of the sun, position of the Earth, perhaps. Here's the Euler-Lagrange equations for the center of mass position, which gives you non-accelerated and basically uniform rectilinear motion. So this is the motion of the center of mass of the sun and the Earth system, just cruising through wherever, ignoring, of course, the other planets and the pull from Andromeda, stuff like that. What's that? Oh, no, that's accounted for. That's next. So we've proved previously that, and this, I guess we haven't proved this, but where I usually give this talk, it's been proved. If the force is directed along the radius, then the resulting motion falls onto a particular plane. So without loss of generality, we can put z equals to 0 in the relative coordinate system. And so the motion is described by just x and y. So we've got the center of mass motion, and then over here is our reduced mass and our relative velocity squared. Okay, here I'm using a little Frenet frame stuff. Basically, if the force is proportional to r, then F being equal to ma, r is proportional to like dv dt, which forces the binormal to be constant, the torsion to be 0, and consequently the motion to be planar. This we might have worked out in Calculus 3, Sam. It's very possible. So anyway, what you do is you use polar coordinates, which I'll use r and theta today for. And so there's the Lagrangian of the reduced mass, the relative part in polar coordinates, just this, r dot squared plus r squared theta dot squared. And so the other Euler-Lagrange equations that you were wondering about, Travis, these ones, these describe the gravitational attraction between the sun and the Earth, for example. We get that mu r double dot is minus partial u partial r plus mu r theta dot squared. And we get that partial L partial theta dot is this. And that's very important because that means that whatever's in here is a conserved quantity, it doesn't change with time. And that, of course, is nothing more than angular momentum. There you go. That's one of Kepler's laws, essentially, that angular momentum is conserved. That, it amounts to that equal areas swept out in equal times, right? But that's conservation of angular momentum right there. And then the radial equation, this is kind of now we start to get into a rather specialized bag of tricks to solve this equation. Okay. So you're putting in, we know that theta dot is the angular velocity, angular momentum rather, divided by mu r squared. So I can rewrite the radial equation like so. And if you tilt your head and squint, you can see that that's really ddr of this thing, right? I mean, obviously. Is that obvious? Maybe it's obvious, maybe it's not. If I differentiate that, I get a what? I get a minus 2 L squared over 2 mu r cubed, right? Differentiating, which is what I had back up here, right? Because I've got an r to the fourth r divided by r to the fourth, which is an r cubed. So then that is an r cubed up here, and the 2 and the 2 cancel. The 2 from the differentiation. Oh, come on, don't go. Don't go. Don't go. The differentiating 2 and the 2 that's here, they cancel, and it's an identity, right? I'm not saying anything especially sophisticated here. Like, this is a straightforward step, actually. But the point is, this is basically ma in the radial direction, right? it's equal to the derivative with respect to r of this quantity. So this is effectively a potential energy for the radial force. You can think of it this way. It's partially a lie, right? Because this is actually a coordinate effect. It's not an honest-to-goodness potential energy, but it's an effective potential. Physicists will call it an effective potential. So anyway, then you do the usual thing, multiply by velocity. When you multiply by velocity, magic happens. You're able to rewrite it as a total derivative. And this is actually a conserved quantity. This conserved quantity is the energy. There's the speed, the potential energy, and then this basically rotational kinetic energy piece. So energy is conserved. And so we have the total energy is that, the effective potential is this, all right? And so you can study then what the possible motions are for a given potential. I still never told you what u was. We've been doing this for an arbitrary u as a function of r. Typically, u is given to us to be the Coulomb potential, which is what? Something like m1, it's m1, m2, g, big G, gravitational constant, divided by r, right? Then you take the gradient of that, and that gives you r squared along the radial direction. So this is a little bit more special stuff here. So we've got this conserved quantity, that conserved quantity. These are the conserved quantities for the central force motion. And let's see here. Basically, we have these two simple differential equations which are possible to solve once we specify a u of r. We've got to solve this, and we've got to solve that once u of r is given. All right, great. But here's the trick. You can actually trade r for 1 over r, which typically is denoted by u, because if we look at u equals to 1 over r, then this equation can be rewritten by this calculus right here, okay? After a little work, not that interesting, let me just go past it. By making a substitution of the reciprocal of r instead of r, you get to this differential equation, the so-called orbit equation. Get to it eventually. Here it is in a box, all nice and pretty. This is the orbit equation. Check that out. That's beautiful. Or to quote my son Matthew, it's beautiful. It's a constant coefficient second order differential equation. And then, I mean, this is what it is, but man, this is nice, you know. And that's the orbit equation. And you can solve it for given choices of f and see what possible orbits are. So, let's see if do I actually have? So here's the most important case. F of 1 over u just works out to minus ku squared. So you end up trying to solve this guy right here, which is just an ordinary, has solutions, you know, like u naught cosine of that plus that. You find that particular solution. Therefore, the equations of motion are this equals to that, which means that r is equal to 1 over u naught cosine theta plus theta naught plus that. And this is the equation of a conic section in polar coordinates. And that includes, this is how we get elliptical orbits of like planets around, not the center of the sun, but actually the center of mass of the planet-sun system. We just tell you that the center of mass is at the center of the sun. That's our cheat in Physics 231. And it does save us a considerable amount of effort, right? Because this would be tough to derive without the benefit of Lagrangian mechanics and this change of coordinates. And it's rather subtle, yeah. But this is, you know, one of a good junior level physics class will spend about a solid week deriving this carefully with a little bit more attention to detail than I've given in here. And, you know, it's just one of those famous problems in physics that all physics majors should know and love and be able to be conversant in. What's interesting is if you go from 2 bodies to 3 bodies, it all falls down. Then it's the 3-body problem, which perhaps you've heard of. But the two-body problem has been solved for some time, and this is it. Any questions? All right. So I still owe you guys some like homework about this stuff, right? As I have mentioned, I was distracted. Yep. Oh, they're already on my website. They're under advanced calculus. If you go down, they're in there somewhere. But I'll send you guys a link because there's a lot of stuff down there. Yeah, I hear you. Okay, so let's see here. So as I forecast, so I started reading this book again yesterday, today, recently, and I'm like, holy cow, I did that. I did that. I did that. Hey, wait a minute, I did that. Like, I did a lot of these things, right? And then he actually, in section 3.2, he has tangent space 1, a geometric definition. And what he does in here is quite beautiful and good. But I think I actually already did it in a little bit more generality, too. I mean, he has taken the time to break into cases. He does it first for a parametrized surface. Then he does it for a graph. Then he talks about a slight twist on a graph. And then finally he gets around to like a fully defined, what I would have called the implicitly defined surface. Like he eventually gets to it, both of the things that I said. But he has decent derivations of these. I have derivations in my notes too, but I think you do well to read section 3.2. I need to make sure we get definitions from here so we can go forward, because he's going to refer to these geometric sets the rest of this our time in this book, right? So we need to kind of make sure we know what he's talking about. So let me see if I can locate them. Let's see if we can just, what is so I mean, in a nutshell, what does he say in section? Let me try to summarize section 3.2. What does he say a tangent vector is in section 3.2? He says, I'm just going to read, if that's okay with you guys, for a little bit. Theorem 3.24. He says, the tangent space TPRN equipped with the operations of component-wise addition and scalar multiplication is a vector space. Yay! I have proved that for a parametrized submanifold of Rn, right? And also for a level set, right? Now his proof for the parametrized set is given here on page 77 to 78. And then in section 3.2, I think, oh, I'm sorry. I'm jumping the gun. In 3.2, he doesn't even talk about geometric sets yet. 3.2, he's just talking about Rn itself and about a curve in Rn, picking a point in Rn, and then all different vectors at a point. So he picks a point, right? And he looks at curves through that point, right? And he says, so the curve is what? C. And so VP is C prime of 0, basically. That's what he says, right? And he says that the, how does he say? So his basic point in section 3.2 is that the tangent space to P of Rn is a vector space. All right? So to make the connection with my previous notation, I think I called this V sub P, right, for the vectors attached at P. His notation's a little bit different than mine, but pretty close. Section 3.3. That's kind of all I mean, it's a lot of what's in that section. Now, But you definitely read this section. Like the first page in the section, he says some very important things about the idea of what we're doing. So the basic thing we have to free ourselves of at this point, and I'll try to get to this by the end of today, is this idea that, I mean, for us, the derivative is the best linear approximation to a function, right? But we were still thinking of that linearization in some sense as being a function on Rn to Rm, right? The next step in this progression of ideas is to think about the derivative not acting on points anymore, but acting on vectors instead. So it's very much tied to this thing we do where we identify points in vectors. So the fact that we can talk about the derivative mapping it being connected to the linearization directly, that is born of the fact that we're identifying tangents. We were identifying vectors and points. And he has some very clear, helpful comments at the section of 3.2. You should read what he has to say there. I think it's better than what I just said. Section 3.3, he introduces this fuzzy notion of a geometric set. What's a geometric set? So I would say that this is, to a pretty good approximation, what I called a submanifold of Rn, right? And he does a few different things in section 3.3, right? He talks about like a parametrized one, right? Parametrized S, essentially. I'll try to be a little bit less vague here in just a second. Just getting the big picture before I forget. Parametrized set, he does graph, right? And then finally, towards the end, he gets to a level. He talks about level set. Really, a hypersurface is what I would call it. And then finally, he gets to the big bad general level set. So in my notes, I pretty much just went straight to big bad general level set and this, because those two things encompass everything. But he has some substructure. He's like, what about a graph? What about a hypersurface? And that's important because a lot of examples really do fit into those middle two categories. And in each one of these viewpoints, he explains what the tangent space looks like. All right? And let's see here. But you know what he said in section 3.2 is the other thing he said in section 3.2 is essentially that we get tangent vectors to a point how? Where do they come from? They arise as the velocity vectors of curves through the point. Now, since we're in Rn, that's not, it's all possible smooth curves through that point, basically. But down here, the tangent space to these geometric sets, it's given by curves which lie on the set. So what it means for the curve to lie on the set is different in these different setups. But he proves for each one of these setups that there's a well-defined tangent space and also how you can build it from the given data, which is just what I did in the notes as well, right? I showed either we can build it from the columns of the parameterization map, right? Or from what? The, how's it go? Is it the perp to the, something awful in terms of the level set formulation, right? The tangent space is not in the Jacobian, it's actually the perp to the Jacobian, right? The level function directly gives you the normal space for the level set viewpoint, right? So if I wanted to get my paws on the tangent space from the level set, I need to do some kind of sneaky stuff. He has a way of packaging that without talking about orthogonal complements in this section, though. There are other lies. The other overriding lie in section 3.3 is he's working with curves. The truth is, what he's really working with are equivalence classes of curves, right? So that's the other sort of rub here is all of these really should be talking about equivalence classes of curves being what a vector is at a point. He has a homework problem about it. Maybe that will happen to you. I don't know. I'm not sure it's an interesting homework problem. Maybe I should just work it for you guys. All right, so let me just, what do I mean here specifically? So he defines a few things. One of the things he defines, and we should make sure we have a definition for here. Definition, U, a subset of Rn, is a domain. What does it mean if we call U a domain? This is a nice term. If U is an open, connected set, subset. So he assumes that the domain of a parameterization is a domain. Okay, sorry, it's awful. So here's his definition. Let U a subset of Rk and phi such that, see, if I had more foresight, I should have abandoned my notes about a few lectures ago and shifted over to here. Oh well. Sorry guys. You had to suffer my notes. Let's see here. Although there's something missing from this chapter in terms of the calculation, the orthogonal complement idea, the normal spaces, Lagrange multipliers, none of that's in here. Let this be a what? So Sam and King, you guys should be happy. You're getting all the technical, some of the technical nuances that you dreamed of are coming to us in this section. It's very, very happy. Smooth, be a smooth, one-to-one, regular. So what does regular mean? I'll define that in a second here. A parametrized set S equals to phi of U yeah. I think I don't know, he's got a long sentence here, but I'm just going to say parameterized set is S equal to phi of U. You know what images are. The question is, what do we mean by that term regular, right? Oh, the parameterized set S equal to phi of U is defined to be the image of U in Rn by phi. Oh yeah, I'm getting there. Yes, correct. So the blank we're about to fill in is really the technical, okay, one-to-one, smooth, but regular means that, meaning d phi of p must be 1-to-1 1-to-1 linear map for all p and u. Honestly, I'm sorry, like some of this to me seems very redundant. It must be 1-to-1 for all p and u. I mean, we already know this right here is the Frechet derivative. It's the differential of phi, right? So we know that that's linear at each, for fixed p, that's a linear map, right? But he's like, I think he's being pedagogical in this definition. He's like reminding us what these words mean. He also has included in the definition some words to explain what this means. He says, geometric set is the image of u under phi. Well, that's already present by writing this, right? So just now, what does this mean? What does that mean, 1-to-1? Right. So this, if we were to look at, I mean, so the kernel of d phi of p must just be 0, right? Equivalently, this is entirely equivalent to saying that if we look at phi prime of p in the Edwards notation, in other words, this is what I was calling before the Jacobian of phi at p, has linearly independent columns, right, for each p in u. I mean, this is what we said before. So that condition is called regular. Now, he has two actually pretty nice examples to illustrate how to find the tangent space for a regular map here in section 3.3. I will not attempt to represent those here. And like theorem 3.36 says that, oh, I'm sorry, definition. Excuse me guys, I'll get it eventually. Definition. Let S equal to phi of u be parameterized set. And P be an element of S. The tangent space. All right. To S at P is denoted TPS. And here's its definition. TPS is what is it? It's equal to VP in TPRN such that there exists a curve from I to S, smooth, with C of 0 equal to P and C prime of 0 equal to V sub P. What do we mean by, and then he gives the, there's something a little bit funny there. The question is, what do you mean by smoothness of this C, all right? So here's a picture. Here's U. Here's S, right? So here's C. Now he's careful. This is the image of the curve. So this, what I just drew, is not the. I mean, this is technically C of I. C of I is a point set. It's a subset of S. He makes the point of saying that the curve is the mapping. This is his viewpoint. But okay, so actually over here is 0, and this is I, all right? And so he says there's a something over here, which he calls, what does he call it, C tilde? C tilde. So C tilde gives you this curve in the domain, all right? And then that is taken over to here by the parameterization, all right? And what do we mean when we say C is smooth? We actually mean that C tilde, which is a mapping from I, a subset of, R, to U, literally a subset of RK, right? This being smooth is something we already have definition for. See, because that's a mapping from R to RK. So when I say that's smooth, that just means that its components are smooth. To say that the C on the surface is smooth, right, means that I can find a smooth C tilde that's related to C in what way? This is the C. C is equal to what? Phi composed with C tilde, I think. So we take a point here, it goes over to here, and then finally over to here. So that's what we mean. I mean, we have to, that's the thing, is when you start defining things like smooth on a surface, it begs the question, like, what do you mean by that? This is what we mean by it. It means that it's the composite of a smooth curve with respect to our regular parameterization of the geometric set. Okay. And then his next theorem proves that this tangent space to P at S is in fact a vector space of dimension what? Just dimension K. Now you are thinking about the next thing. Yeah. On the, oh yeah, that's a T. I'm sorry, it's, yeah, those are just T. It's not. I gotcha. No, yeah, that's a T. And then that's C tilde of T, and then that's phi of C tilde of T, which I have written in a spot which is hard to read. Yes?
What do you mean by C prime 0, like differentiate at boundary? I mean, C prime 0. It's just saying that the BP is a tangent line, a tangent vector. I know, but how can I differentiate at the boundary of it?
Well, zero is not the end of I. It's an interior point to I. We're always working. Our curves are always working with a domain which is got 0 as an interior point. No. I is not. I is just, yeah, good question. I is a generic, some kind of generic open interval, or at least, I guess it doesn't have to be open, but it definitely contains, whatever I is, it definitely contains an open interval about 0. That's essentially the what's needed to make clear that comment he has about germs later. But anyway, he has a useful sort of transitory definition at the start of section 3.3. He says this: the geometric set S is a set having the property that for each point P in S, there's a vector subspace TPS, subset of TPRN. Moreover, these subspaces should vary smoothly with P and should all have the same dimension. So this is kind of his transitory, fuzzy definition of what it means to be a geometric set, is that at each point you can find a tangent space, in that tangent space has equal dimension over the whole surface, which is what I said, isn't it? Remember I said, what's our definition of manifold? It should be such that like whatever it has some kind of idea of dimension, which means there's a one-to-one local correspondence with that space in RK, whatever the k-dimensional manifold is. So he's saying the same thing as I was saying, albeit in a slightly different notation. And then, like I said, the rest of the section, he goes on to develop graph, level set, and big bad general level set. I'm not sure if I have the patience to do that at the moment. Because I think you guys are getting bored with this, but am I wrong? Should I continue? I could jump ahead. What's that? It's up to me? All right, I'm going to jump ahead. I mean, his proof is, let me just at least give you the definition for each one of these objects that I should do. I need to copy this. I'm going to get eraser dust over that, but over this book, and it hurts me to do that because this book is beautiful, and I hate to malign it. Curses. Come on. So his next definition, he has definition 3.312. Here he has U, a subset of R n minus 1, all right, and a domain, all right. He has F that goes from U to R, so it's a real valued function of n minus 1 variables, all right, smooth. And then he says SF is equal to the graph of F, and he just defined that before this definition, but I'll define it here. So the graph of F is what? You do x1, x2, dot, 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 xn minus 1, and then what goes in the nth spot? F, right? Let's say f of x, such that x equal to is an element of where? Well, the domain of f, which in this case is u. So this is a graph. It's exactly what we call a graph in Calculus 1, Calculus 2, even Calculus 3, right? Great. And so this is going to be the graph of f. He says let P be an element to the graph of f. And then he is going to define the tangent space to SF at P. It's going to be a subset of TPRN. Here's what it is. VP element of TPRN such that what? There exists curve from I subset of R to what? SF, yes. These are all the same. It's always the same thing. Every single one of these stupid definitions is you take the curve to lie on the geometric set, which in this case is the graph. And then C of 0 equals to P. C prime of 0 is V sub P. Now, King, I know you're wondering what C prime of 0 really means. He has given the careful definition in section 3.2. But it is really just the velocity vector attached to P. All right. And then the theorem he proves shortly thereafter, theorem 3.3.13, what's he have? He has that the tangent space to P at SF, well, first, the tangent space to a graph is in fact a vector space, and it's an n-1 dimensional vector space. All right. All right. And he also shows, he also has a, he has a little bit more than that. And in the next theorem, in 3.14, he proves that, in fact, that the tangent space to P at SF, you can write it as follows. You can write it as A1 through AN minus 1 comma AN at the point P such that, and here it is, A sub n is fixed by the first n minus 1 of them according to the following formula. Sum I equals 1 to n minus 1 of A sub I partial f partial x sub I at P. Oh, I'm sorry, not at P. Annoyingly, where? At P tilde. Where Yep. P is equal to P tilde, comma f of P tilde. And of course, P tilde is an element of U. This is also what I did. I found that if we look at the big bag level set, you can construct the tangent space by knowing the first k components of the tangent vector, because the last n minus k of them are fixed by the local function which solves the level set condition. And then the implicit derivative, the implicit function theorem, forces the relation between the first components of the vector and the last components of the vector in this way. Now this is a special case, of a graph, but it's kind of the same stupid thing. I don't know. I'm getting very tired of this section. If you don't mind, I'm going to put the book away for a little bit and misbehave if it's okay with you guys. For I have not behaved enough and written enough things down on a paper from the book to be productive, and I should misbehave a little bit in here. If I'm not going to misbehave here, where will I misbehave, right? But please do read the rest of section 3.3. It's kind of important, and it also should be, well, I wouldn't say easy reading. That's too strong. But all right. So I see I'm torn whether or not I should just, I better, I'm very tempted to tell you guys what a manifold is and define the tangent space for like a general manifold. But I guess the point of having this book was to not do that. So I must bide my time. I'll do it eventually, but not yet. All right. So, section 3.4. This is still on the tangent space. But this is what he calls analytical definition. And so he basically points out the following thing. He's like, if we have f from a domain to R. All right? Smooth. Containing P containing U, all right? P a point in U. And if we have C, right, which is a curve, a smooth, say a smooth parametrized curve from I to Rn, right, such that C of 0 is equal to P, right, then oh, I'm sorry, I've forgotten a very important, very important little side note here. Where is U? Right. Thank you. So in this in this context, if we look at ddt of f of c of t, what happens? Say at time 0. We get what? We get the gradient of f, right? At c of 0, dot product with, c prime of 0. That's the chain rule. Now we can rewrite that. I'm sorry. He has a little bit. He makes it look like. We can also write this as df, right? This is df. But the point here is that this is really the gradient of f at p dot v sub p. Let's see here. Nothing terribly shocking there, I don't think. So here's the thing that kind of makes you go, what? So he goes, okay, so what we can do then is we can look at VP as an active object. We can look at VP as being something that does what? It takes in the function f, right? Takes in a function f, and it spits out a number, right? It spits out the number gradient of f at p dot vp, so to speak. Let's see here. So here, this f has to be in what's called CP. I guess I don't know what the right letter to write is here at this point. Maybe CPRN, I suppose. And what that means is it's smooth near p. So we can calculate the derivative of the function at p. All right. And to be more pedantic, it's a smooth smooth near p, it's real valued, okay? I'm talking about functions from real valued functions. This is kind of a shocking thing. Like I've gone from telling you that tangent vectors are, you know, what they're tangent vectors to curves, right? I mean, we start by telling you in physics that you can move them around and can identify them with points. Now we're saying don't identify them with points, right? Then I'm telling you, well, they're tangents to curves. Now I'm telling you that they're some kind of function that takes in a function and spits out a number, right? So like, make up your mind. What's a tangent vector, right? But this is probably the critical hurdle to get over in differential geometry, to get used to, is this idea that we can either think of tangent vectors as literally geometric tangents to curves, really equivalence classes of those, or we can think of them as these active operators. So this is this viewpoint here is, and so there's something confusing. I'm not totally sold out. I mean, he refuses to use different notation for these different objects in this chapter. He says he's just going to call them all the tangent space, and it'll be clear from context which is which, you know? I think it might be fruitful, helpful, and useful for us to spend a day talking about all three different perspectives and the isomorphism between these worlds. Yes? Okay, so I'll plan on doing that next time. But here is his definition of, I think he's calling it an analytical tangent vector. I usually would call it a derivation. Let P be in Rn, all right, a tangent vector at P is an operator Vp C infinity P of Rn to R, satisfying the following three properties. Number one, for all f and g in Cp infinity Rn, we have that Vp of f plus g is equal to Vpf plus Vpg. 2, for all f in Cp infinity, man, I should have come up with a shorthand for that, good grief. Oh. And C in the reals, we have that Vp of Cf is equal to Cvp of f. So basically, what does 1 and 2 say? Right, it's a linear transformation. It's additive, and we can pull scalars out, right? It's additive, homogeneous. And then finally, again, this is hurting me. You know what? For all f g in Cp infinity Rn. What's he doing to me? Good gracious. There. This is what happens of me not writing notes before and just trying to work out of a book directly. It's a beautiful book, but it's not set up for lecturing, you know? Goodness gracious. And then Vp of f times